Okay, so there's Krishnandan Avtar. I'm a PhD candidate at the Aerospace Engineering Department, ISC Bangalore. So I'm offering this course as a sequel to a previous course on Introduction to Differential Geometry. So I had wanted to extend it to the ideas that we had discussed in the previous lecture series to applications in mechanics, particularly solid mechanics is where we are going to focus on. So as you may have known from the flyer that was circulated for this course, so broadly, so what all do we intend to cover, right? So the contents of this course. So broadly, we are dividing this course in into three modules. So and of course, many a time they will overlap. It won't be linear in that sense. We will always go back and forth between some of the modules as we discuss along this as we progress through this course. So in module one, I plan to review some of the fundamental ideas. In essence, we are going to review differential geometry. And principally, some of the final results will not be deriving the finer details in this particular review, since that's not focus for the current course. We will be mainly looking at some of the results, the final results that have been derived, the expressions, the definitions, and how can they be applied in various scenarios. So that's what we are going to cover in this differential geometry, in this review of differential geometry. So we would be covering ideas of curves. So of course, the parametrization of a curve. Then we look at the most used one, which is arc length parametrization. And I would be only giving you the definition for about, and we would be using arc length parametrization throughout this course. And then we would be talking about curvatures. Also discussing about some planes, some different types of curves. Broadly, they are plane curves and space curves. We'll look at some of the different frames of representation of a curve. So the very celebrated Frenet-Serre frame, and one is a modern system which is what we call as the director basis or director frame. This is mainly to um, avoid falling into some of the pitfalls of Frenet-Serre frame. Right. This is what we are going to look at. Then we'll follow it up with surfaces. In surfaces, our goal would be to understand how are they parametrization of surfaces, and look at the requirements for uh, the smooth surfaces, as we call them, smooth surfaces. And we'll be then talking about some of the very relevant ones, particularly ruled surface. And then we would venture into the ideas of first and second fundamental forms. Fundamental forms. And then we would be talking about curvatures of surfaces. how do we define curvatures as if, I mean, based on the idea of a circle, sorry, or a curve embedded in a surface, and we look at the curvature of the curve itself. So that is an easy way of approaching, trying to understand the meaning of a curvature of a surface. And there are various such curvatures, various such based on our requirements. So typically, we tend to uh, learn about the principal curvatures, and then follow it up with, say, Gauss curvature, and also what mean curvature. And if we look at the curvature of curves embedded in the surface, then we tend to define what we call as the normal and geodesic curvatures. This typically for if a curve passes or lies in the plane in the surface, then we tend to define this normal and geodesic curvatures in such scenarios. Right. And the second module, we would be taking a look at some of the fundamental ideas in tensor calculus. So here we would define what a tensor is, definition of a tensor, and and then, as you may know, uh, that even vectors, tensor, and the rest of things also, I mean, that's how we define a tensor, right? So we start basically, scalar is the simplest tensor. So we have this scalar, a vector, and say other higher order. And so they all of them tend to be called as tensor broadly. And then we would look at some of the tensor operations, like differentiation and all that. Yeah. Differentiation and all. Then we have this look at different sorts of coordinates, the coordinate representations. Most prominently, we typically you tend to use this Cartesian coordinate system. However, it so happens that this Cartesian coordinate system is not helpful in many applications. Say if you want to perform calculus on some, say, arbitrary manifolds, arbitrarily smooth manifolds, then typically we would like to define a coordinate system in which it is much easier to represent some of the quantities, right? Such as, say, trying to determine the strains, strains, stresses, trying to differentiate along on all those manifolds. Then we will have some sort of a generalized coordinates, and that's what we call as the curvilinear coordinate system. Hmm? So one of the idea is that in Cartesian coordinate system, it's the components along one direction are independent. You can very well represent it. Uh, you can perform operations on it independently of the other coordinates. However, in curvilinear coordinates, we do not have that freedom. in that the differentiation in along one of the curvilinear coordinates will tend to use the variation along different curvilinear along another curvilinear coordinate as well. So that makes it a bit complex. And there is where we will talk about things like representation of such as say this covariant and contravariant representations. So write it covariant and contravariant basis, right? And once you have covariant and contravariant basis, then we can do all that. Uh, we can determine the derivatives, determine the derivatives, uh, of namely both the covariant and contravariant and contravariant derivatives. And in this meanwhile, we would be utilizing what we call as a tool called as a Christoffel symbols. So this is about what we plan to cover in tensor calculus part. And then we will talk finally about the applications. Module 3, we will talk about the applications in mechanics. So here at the outset, I would like to discuss about elasticity, concepts from elasticity. From say theory of elasticity essentially. More from an engineering sense, we would be talking about how do you define the linearity, right? Linearity or linear elastic. What do we mean by linear elasticity? And then delve into things like we have this linear elasticity. Then how do we construct energy functional, particularly what we call as the strain energy functional. That's what we are going to deal with, and slightly discuss about some of the beam theories. Just the Euler-Bernoulli beam is what we will look at. In very, we'll just try to cover the overall aspect. We won't go too much into beam theory, just how it's formulated and all that. So how do we formulate energy functional for the case of Euler-Bernoulli beam theory? Then we move a step forward, and then we would talk about uh, then we would talk about some of the red theories. At first, I would like to introduce what are called slender structures or the elastic slender structures. Elastic slender structures. They are mainly rods, ribbons, plates, and shells. So these are the. I'll introduce the elastic slender structures, and then we would discuss about the mechanics of all of them. Principally, we would be dealing with rods and ribbons, and partly on shells, right? Because the study of cells require a complete course in itself. So we'll try to cover as much cells as possible. Then mechanics of all of them, mechanics of rods, ribbons, and shells. That is this is the overarching goal of the course that we have that I have designed, so to speak. And in between, we would use tools such as Mathematica, principally Mathematica, to code some of the derivations. And Mathematica is a symbolic software to analyze, or to symbolic software principally to for manipulation of you can use essentially to do all the analytical stuff, right? For say analytical derivations and all principally, but of course now this Mathematica has given quite a bit of numerical functionalities. But however, we would stick mainly to for analytical derivations and then visualization purposes. So that's what we would be dealing with Mathematica. As for references, uh, so what are the references that we are looking at? So we'll have broadly at the outset. I must give the my my notes on for the previous course that I had offered, which was Introduction to. Okay, my notes on Introduction to Differential Geometry, which I'll share through that folder where all the course materials would be posted on. This is just for review purposes. And then as for books, which of course I had followed in even in the Introduction to Differential Geometry course, but here I would stick mainly to elementary differential geometry. This is by Andrew Priestley. So this is one book of the several available in the literature. And the second book, which I will be following for tensor calculus, is a book called Tensor Analysis. With applications in mechanics. There is a book by L.P. Lebedev. It's L.P. Lebedev and Michael Cloud and Victor A. Eremeyev. It's a very nice book on tensor calculus. And for rest of the things, maybe I will also follow a little bit from a book called Elasticity and Geometry. Some of the ideas on slender structures we would be uh, referring to this book by Orderly, Basil Orderly and Pomio. And Pomio. And we would be for theories and all, we would be principally looking at journal papers. So there is an area of still, it's not, I mean, it's still under research, though not very actively because only very few groups still study slender structures, particularly emphasizing on model development. So papers mainly by orderly and some papers by uh, Elliot Fried and papers by Rick Pedro Group, by Pedro M. Rice. So these are some of the papers that we'll be following for mechanics of rods, ribbons, and shells. Yeah, so this was about the references. And regarding distribution of hours, I will try to finish or review the all the requisites to finally discuss about the applications part to as soon as possible. Maybe few lectures, if three or so total we have 14 hours. There's a 14 hours course, so we will. So there are 7 lectures scheduled for 2 hours each. Of course, we would not be fully doing it for 2 hours. Mainly, not more than say 1 hour and 40 minutes max per lecture. And so, say for the first 4 or 5 lectures, I'll plan to finish the differential geometry part and say 4 lectures, 3 to 4 lectures on differential geometry, then tensor calculus, 2 to 3 lectures, and the rest will be dealing with models. But we would always be going back and forth. So there is not a very rigid course structure. We would be always going moving back and forth. So wherever the need arises, I'll introduce the ideas of uh, some of these mechanics aspects.
So, can you suggest a course homepage wherein I find the course notes, maybe of some other instructor? Wherein I can take the printout of those notes, and which are not very thick. I mean, say some 100 pages. Uh,
You mean books, huh?
not the books, but the course home pages. I mean, maybe of some other university or some other instructor who have which you would like to refer and which are close to the topics covered by you, and whose printouts I can take.
Okay, that unfortunately I mean, I am not following any particular course from anywhere,
Okay,
and as I am aware of, um, the course materials for such topics are very scarce online, and so that is the reason I'm going to mostly follow books, and and also that I want the session to be say some sort of a discussion so that we can clear doubts directly during the lectures itself.
that's fine. I hope that I mean you would be sharing your notes in such a way so that I can take their printouts.
Yeah, okay. So the previous, I have the lectures notes for the previous course on Introduction to Differential Geometry. So I will put in the folder that I have shared with all of you. So that lectures can be used, but again, that course was specifically for differential geometry, and here we would not be going as deep in the previous course because this course is mainly for understanding how the concepts derived from differential geometry are used in mechanics, particularly solid mechanics, and in that also looking at slender structures. Because in slender structures, we typically there is where we use ideas from differential geometry. So that
Okay,
is where the situation here is here.
all right,
Yeah.
thanks.
So yeah, could you please know what's your background in terms of what the course that we are like background in differential geometry, if any?
So as such, I do not have any background in this subject. Rather, all the topics which you mentioned till now are somewhat new to me because
I see.
I'm from the computer science background and that too from the theoretical computer science. But then I'm very much interested in understanding. I mean, like the topics like manifold. I do not know what a manifold structure is, but then I read this thing in some of the topics of mine.
I see. I see. So do you have interest in computer graphics by any chance?
No, no, not as such, but then I will try to follow. I mean, what you deliver in this course, and I'm sure that these topics would definitely be helpful to me in the topics which I might not have read so far.
I see. Yeah, 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 that. Yeah, because there are certain groups, right? People who work in computer graphics, they tend to use a lot of ideas from differential geometry. So there
Yes.
are groups by Keegan Crane. Keegan Crane, he is a professor, I believe, in CMU, if I'm not mistaken. I think he is in, yeah, Carnegie Mellon University. So he does a lot of differential geometry to design algorithms for computer graphics.
Okay. I
Yeah,
see.
there is one such group, and even even Audley has worked with some other guys, specifically some other professors who deal with computer graphics. So there is where the application of differential geometry actually are used in practice.
Okay.
So
Okay.
yeah, that's how it is. So there was a very seminal paper long back in 2007. It was published in this uh, ACM Graphics Forum. The paper is called as the discrete elastic REDS. So the paper is called as discrete elastic REDS. It's it was published in some this in this some SIG. I have forgotten the particular conference, but it's a very seminal paper for the reason that even now. Okay, so it was published in a conference and then finally in this journal called ASM Transactions on Graphics. So there is a once one of the principal authors was this Ethan Greenspan. So he also is a computer scientist currently, I believe, in University of Toronto, where he's continuing his work on computer graphics. So this particular tool was also incorporated in Adobe Photoshop for some brushing application. So the algorithm that was discussed in this paper.
Okay. Okay.
Yeah. Okay. So now I'll just start discussing about let's begin our study with curves. Okay. So today is this is the lecture one. So here we'll discuss about ideas of curves. And I'm sure all of us are aware of what curve is. It is such a it's so ubiquitous, and we have been familiar with it since our school years. So fundamentally, even line, as you say, even line is a curve, right? Fundamentally, it's just that it happens to be a curve with zero curvature. And then you have the standard curves, any arbitrary curve, right? So all these are typical curves, as we call them. They can be of various types, can be open, like this is an open curve. Then you can even have some closed curve. You can even have some helical curve. And there are such infinities possible with regard to how they appear in nature or even in our mathematical studies, and even some of the structures. Say, for example, we have all these cables, electric cables, wires. They all tend to be, they are all idealized to be curves in a mathematical sense. And before we start even start this the discussing about RUDs. So a RUD is a physical object which are present in various forms, such as we discussed curves, I mean in the cables and all. However, we can always idealize them as curves from a mathematical sense. So although if a rod, although it has some finite diameter, say this, let we have this, say some segment of a wire, it has some finite diameter, and but the diameter is much smaller than the length. So this is the length. So it's much smaller than length, because of which we can idealize it to just a curve. So we consider the centroid of every face of this of the cross of every cross section of this segment of the cable, and which gives us the center line. And we force all the properties of the cross section at every station on the center line itself. So we only extract the center line and perform our entire study just on the center line. And center line is nothing but a curve, right? So that's how we move from an engineering, an object in real life, and we, from an engineering perspective, we have this cable, and we just reduce it, what we call as dimensionally reduce it to a curve, and then apply whatever we learn in the theory of curves to study it. So that is the overall idea of studying curves from an engineering perspective. Now let's define, or we define what we call as this word called parametrization. So parametrization is just some systematic way of defining a curve, right? Here for a line, as we saw, given a Cartesian coordinate x, y, then we can represent it as some y is equal to mx plus c, where m and c are both scalars, and x varies from, say, some lower limit to some upper limit, right? So say, okay, let me draw it here. Okay. So this is a curve. This is y is equal to mx plus c, x, y, and then the limits of the interval for x is x naught to x naught. Right? So this was for a straight line. For a general, say for example, you want to draw for a circle, right? So circle of a unit radius with center at 0 at the origin can be written as x squared plus y squared is equal to 1. But the thing is here, when we try to say express y explicitly in terms of x, then we write it as square root of plus minus of square root of 1 minus x squared, and it becomes so difficult. Like if you take only the positive part, then you are only representing the upper segment in the upper plane, and if you take the negative part, then you are representing in only on the lower plane. So the issue is that there is always happens to be some, say you are just, although it was a closed curve, you are still having it to break it down into two segments or two arcs or two semicircles. So we would want to formalize it in such a way that we can move along this circle starting from here and move along the circumference itself and then return back to where it started. So we would want a representation of the circle in that form. And there is where this parametrization comes into place, that we can travel at start from any point and then travel along the boundary of the circle and return back, return from where we started, right? So the way we what we understand by parametrization here is that, say, let me give this mathematical definition. So parametrization. So the definition for what we call as a parametrized curve. What is a parametrized curve? Right? So parametrized curve in Rn space. Rn space means it's a vector with n components, right? Rn space is a map gamma vector from alpha comma beta to Rn for some alpha beta with the limits being minus infinity is less or equal to alpha is less than beta. So we are using the extended real line. And the interval alpha beta, and since you know that very well that there's an open interval, because in this interval the endpoints alpha and beta is not part of the set. So this will be t is an element of R where alpha is less than t, which is less than beta. Okay, of course, the lot of jargon is here. So here we are first we need to understand what is a map. Right? So let's break this definition down into simple components. So map. So map is essentially a function which takes some input, some argument in this sense, and returns some object. It takes some argument and returns some object. In a sense that you can call it that it's something which you have this some set X, some set Y. So how the elements of this set are related to the elements in Y. So this is called as a map. Right? And map function, they mean the same thing, right? So this was one thing. And then we see that it says that gamma vector from alpha to beta is an element of R. So what it implies is that in simple terms, we can say that gamma is a vector valued map. It's a vector valued map, which means that it gives us a vector, although the but its argument is a scalar. So which means that gamma vector takes argument as a scalar and gives a vector. And in this case, it belongs to Rn. So in a sense that you have this say interval alpha beta, and you can map from any point to some, say, some vector. Right? Say in this case, let me present an idea of R3. So R3 means three-dimensional space. So here it will be some vector. So some vector here, and let this be t. Right? So it's as if it's taking gamma vector, taking t as an argument and mapping this point p vector. And this p vector has three components. Right? So p vector has three components which are x, y, and z. Again, to be mathematically precise, it is actually x as a function of t, y as a function of t, and z as a function of t. So overall, even p vector is just that point, and in all these cases, t is fixed. Right? So what you saw that you took scalar as an input and you got a vector as an output. Right? So that is what we are talking about map here. Now you'll ask, okay, but I'm only showing the points. How does it give us a curve? Now, what you see is, I think for a better representation, I'll just use R2 space, which makes things slightly easier to visualize alpha, beta, right? And you have this R2 space. And you know very well that as per the map, alpha is not included in the set, right? So it is like you have open. So alpha is not included, beta is not, which means that t can take t, let's consider it to be some running variable. It can take value anything which is infinitesimally greater than alpha. So say some this point we take and we map it to some point here. I think I should use a different color. So you have this and you have this point here. So this is one point, right? And then likewise, say at some different point. So this, let's take it to be T1, this to be T2. So T2 is being mapped here, right? This is T2. And likewise for T3, T3 gets mapped here. And likewise, so eventually you have Tn, it will be mapped somewhere here. And I can connect all of them. Right? All of them is connected. So which means that although the map was throwing just the points, but as we decrease the spacing between this increments in t, so t1, t2, as we reduce the spacing between them, even so gradually even the points here became closer. And finally we could trace. This is also called as the trace of the curve, of the mapping, trace of the mapping or of the curve itself.
So
Right?
I have a
So
question.
yeah.
So since we are projecting a single point over the real line to a higher dimensional space,
Yeah.
so like say, is it possible that when I project the point T1, I project it say in multi dimensions and corresponding to the point T1, I map the point T1 to a plane and similarly T2 to over again a plane, and then when I combine these planes all together, so then I get some curve kind of a thing.
Yeah. So it's like you get, yeah, in some higher dimension. I don't know what you understand, what you mean by plane here, because uh,
So
at
plane,
best, we, yeah.
plane by plane, I mean to say it is say a point which is in more than three dimensions, a hyperplane kind of a thing.
Okay. You could just call it as, say, higher dimension, say some higher dimension coordinate frame. So say Rn, right? And where n is greater than 3,
Yes, yes,
right? So point in that space, in that Rn space, right?
yes.
Yeah. So what you will do is you will trace the points and then connect all of these points, because the separation between these points tend to be infinitesimal as you decrease the spacing in the domain, right? So when we talk about functions, we always have what we call as domain, over which we define a function, and then image. So the points are the corresponding image. The points are the corresponding say values for the points in this domain set. And when we just connect all the points in the image set, then we trace the curve. So it's like gamma vector is not the physical curve. And it really took time for me to digest this fact. Gamma vector is a mapping. what you call as physical curve is actually the trace, or sometimes you also hear the word called graph. So it's a graph of gamma vector. That is called as what you see here. Gamma vector is just some map which can be differentiated, which can be analyzed, right? So like, for example, this cannot be differentiated. This is a physical object. You cannot differentiate it, but you can differentiate the mapping. And there are certain requirements on gamma vector also. Like gamma vector has some restrictions. So what are the restrictions on gamma? The restrictions on gamma is that gamma vector dot, right? So gamma vector dot means d gamma vector by dt in sense, right? So this should not be zero vector, never. This must not be zero vector. Then only we call it regular. Then we call it as a regular curve. And we would always say regular curve. So regular curve is a curve whose mapping, whose derivative of mapping is not zero vector at any. So this is not at the, it should be at any t which belongs to the set alpha beta, to this open set.
So what if gamma is a mapping from R to R?
R to R. Huh?
Yes. So then the gamma dot would be equals to all zeros then.
Okay, so even in that case, say for example, say you are talking about, say R to R mapping means, say we can represent in terms of say gamma. So you mean gamma R to R, right? So let's call it, say it to be gamma T is equal to A T. Right?
Yes.
Simple. We can, this is also mapping, right? So it maps alpha beta to an interval which is A alpha and A beta, right? So this is the mapping by this gamma, right? And you can clearly see that gamma dot is equal to A. So A must not be equal to 0. If A is 0, then it's not a valid mapping. And it's of no use to us. Yeah.
Yes. Yes. Right.
So then it so happens that and any time you choose anything, it only maps to a single point. And mathematically, it would make sense. I mean, mathematically, like you could always make some sense, but differential geometry is meant to study geometry, right? It's meant to study something which can be seen, something which can be felt, right? It's we are dealing with some structure. It's some physical structure, and that's how the origin of differential geometry is. So here, there, what you can say is that you cannot map a small element to nothing. Physically, it does not. It means that you are from a conservation of mass point of view, the mass is vanishing. I hope
Yes.
you're yeah, and because the thing is, you can always derivative is ultimately some delta y by delta t, right? Delta
Yes.
gamma by delta t. Just
Yes.
that here in the limiting sense of delta t tends to 0. So which means that gamma dot is equal to 0 means delta y by delta t is equal to 0. Which means that although you had started with some delta t, but this some delta t is getting mapped to 0. So yeah, it seems that you are vanishing. The matter is being vanished, which is not physically possible, and it also violates all that conservation and all that conservation laws. So that's the reason we don't deal with all these singular points or singular curve. We only deal with regular curves, proper, with whose derivative is never zero vector at any point at any t.
So
And because of this, it will also be smooth. It will also be smooth. So we also want, that is a so we also want the curve to be smooth, or the map must be smooth. This is the second part, second restriction, that because if it's being regularity, we also want gamma to be smooth so that we can carry out other operations. There are certain cases where this gamma dot can be zero. Say, for example, you look at a cusp. But the thing is, here we just then what we do is at least we have this consolation that at least it is not the derivative is not zero anywhere else. So cusp is a some say you have these two curves which meet at some sharp point. So at this point, what will happen is gamma dot tends becomes I believe it becomes zero, or maybe I need to re-verify. Like I may have forgotten, but here, but then what we do is we just exclude this point. Since this is just one point, we can exclude it and still work with the other part of the curve. I need to verify really, like I'm not very sure.
And is this a region that, I mean, the title of the subject is differential geometry, and do we have something like, say, integrational geometry kind of the thing as well
Yeah,
on
there
the?
exists a topic called integral geometry, but that is a very obscure topic, which I believe very few people, if not no one, is doing right now in the entire world. I just got it to know from a Wikipedia article, but it someone had just come up with this, but it seems I have never seen any mathematician with differential geometry as his or her interest. So I believe it was just some imagination. But so ideally, what we talk about differential geometry is the thing is even in differential geometry we still use integration. So I don't know whether if that can that not be called as integral geometry, at least operation in an operational sense. But generally, what happens is differential geometry is broadly it implies that you are trying to perform calculus on manifolds. So that's best you can we can define. So differential geometry from a very fundamental sense is defined as calculus on manifolds.
I hope you would be explaining this term manifold as well in your, I mean, in this lecture.
Actually, manifold tend I am a bit aware of this mathematical word. Manifolds tends to it actually implies all that spaces, right? These are all spaces, all the topological spaces where we talk about sets. How do you define a manifold? So like the fundamental is always topological space. So these are all sets which for us we do not have some any uh, I mean any particular use, except that when we engineering if we call something as manifold, it typically implies some surface or a curve because that's what we are physically able to see. So even this is a manifold. Even this is a manifold. So yeah, contextually, this is how you understand manifolds.
Okay.
So on some such surface, you can always do integration, differentiation at any point of some quantity. Say if this happens to be deformation, if you're looking at the deformation of the surface at any point, so at any point you will have some deformation, you will try to find the gradient and all that. Right. So all that will again, that's how we do, that's what we mean doing calculus on the manifolds. But mathematically speaking, it involves a lot of other words. Like it's based on set theory, then you have topological space, then you go to precisely what is a manifold, and then a subpart of manifold is what we call as the uh, ideally subpart is what we call a smooth manifold. And here for engineering applications, we only deal with smooth manifolds. So we deal with smooth manifolds. Smooth manifolds is where on which the all the so to speak the quantities can have infinite derivatives, all of which are continuous in nature. So I think I would not be able to contribute beyond that, except that these are just some not physically visualizable mathematical structures. So that's what manifolds typically is.
Yes, yes.
Yeah, but for our sense, in this course, whenever we talk about manifold, we mean surface or a curve. So that what manifolds for us implies. Okay.
Yeah.
Yeah. So, okay, we went through these restrictions on gamma, regularity, and smoothness. Now we'll discuss what we call as the length of a curve. Okay, before that, let's have one quick example. So say you have a parabola. Parabola is, say we take this and you have x, y, and this graph to be, the graph is y is equal to x squared. Okay. So we want to parametrize it. And you always know in parametrization is that the whole idea of parametrization is have some quantity or define some quantity or maybe define and it should be like define only one independent variable. Loosely speaking, that's what I'm loosely speaking, only one independent variables and all the other variables are a function of it, are functions of it. And secondly, it varies along the along some coordinate lines. It varies continuously, right? It varies continuously from some interval. So like t should always be an element of scalar. It should always be a real number. And so t must always have some interval of variation. So here, when we take a look at this parabola, so what we see is that you can even just call x as some t. Let's call, say, x is equal to t. And as we know that when we define this parabola, right? Parabola happens to this belongs to R2 space, right? This belongs to R2 space. And going back to our parametrization of a parametrized curve, we always want a map which maps from some interval on real axis to some Rn. So here we have y is equal to x squared actually lies in R2 because x and y we have two coordinates along which in the plane of which we are representing the curve. So we must find some parameter which is a subset of the real line from where we'll map into this space. So let's try to devise such parameterization. So we have x is equal to t squared. Oh, sorry, y is equal to x squared is what we see. So we think, okay, but we also allow x to vary from some, say, some minus, say minus alpha to plus alpha, right? We allow x to vary from some minus alpha to plus alpha. So you can say, okay, so which means that I am able to define some parameter. So can we not name x as something else, right? So let's just call it as t is equal to x, right? And since gamma vector needs to have two quantities, first and second, or gamma 1 and gamma 2, both of which are themselves maps. They are also maps. It will be a function of t, function of t. Right? So here what we can say is you can have for a parabola, let's take the first coordinate to be the x coordinate. So it's just t. So which means that we have y and in place of x put t. So it becomes y is equal to t squared. And so y is the second coordinate of this mapping, second component of this mapping. So it's like gamma 2 of t is nothing but t squared. And yeah, this is one such mapping. Now you'll ask, okay, but is the parametrization unique? The issue is no. Is it unique? Is parametrization unique? Answer is no. You'll ask, but why? The thing is, you for a parabola, all that we need to satisfy is y is equal to x squared. Right? All that's what needs to be satisfied. Then we can even have x is equal to t squared and then y is equal to 2 to the power 4. It still satisfies this relation. Although the fact remains is in our particular scenario, we even allow x to have negative values. But here we are restricted from it because t square cannot be negative. So if it were some other, if we had restricted to just this part of the parabola, just this part, then even this is a valid, this is also a valid parametrization, right? For say 0 is less than, sorry, x is greater than 0, which is less than alpha, then this is also valid, right? So which means parametrization is never unique. So to alleviate this problem, there is where we introduce something called as arc length parametrization, which is not that there is also not unique, but it is unique till some sign. There is only some sign difference. So arc length parametrization is what we introduce in the picture. So the way we define arc length parametrization is uh, so this relies on a fact of length, the concept of length of a curve. So it's related to the length of a curve. And we know very well that the length of the curve will always be unique, right? Because we are talking something physical, some physical aspect of of a curve, which is its length. So the idea is, say you have this curve. Let's say we have this curve. These are curve. And say it has been mapped from some interval alpha beta from here, mapped into this R2 space. So x and y. It starts from here, ends here. So there's like gamma vector of alpha, and this is gamma vector of beta. And at any point, it is just as if this t, so this is gamma vector of t. So let's fix our originating point to from here. Say let this be from where we start walking along the curve. So we start from here and end it here. This is our destination. So as you move along this curve, you are covering some distance, right? As we are moving, we are covering some distance. So this is the distance. And you know the distance by definition is always greater or equal to 0. So 0 is only when we have not traveled anywhere. Otherwise, it's always greater than 0. So as we are progressing along this line, along this curve, the distance always keeps on increasing. It always keeps on increasing. And you say, okay, so it means that there is something, some parametrization which will be always unique, which can be used, which is unique in the sense that it can only take one value. And then that's how the idea came about arc length parametrization. So it is as if you are covering some length along the curve here, and you just call it the distance, you call it as s. And as when you are at t is equal to 0, at t is equal to alpha, and you can even have this distance as a function of t. So as you are increasing, as you are say starting from t is equal to alpha, at t is equal to alpha, s is equal to 0 because we have not moved anywhere. And at t is equal to beta, s is equal to length of the curve. Okay, now let's first determine the length of the curve. So we go back to our all that Pythagoras or even Euclidean norm of something. So say you have this curve and you take a small part, you take this part and say this is an xy space, xy plane. So this small part, you just say isolate this small part. So this small infinitesimal element along this curve is horizontal projection would be delta x and the vertical projection would be delta y. And you can call the length. So in the immediate vicinity, it resembles a triangle. And you know very well that this seems to be a right angle triangle because if we zoom in, this is how it looks. So this is the segment of the curve, and this is the projection along y-axis and along x-axis. And this we can call it as delta s, which means the length of this curve. So which means that delta s is nothing but it is delta x squared. So delta s squared from Pythagorean theorem is delta x squared plus delta y squared, right? And then we can have, since the length is always going to be greater than 0, we can take square root or only the positive part of square root and delta y whole squared. And then we can take delta x as common factor and we'll have 1 by 1 plus delta x by delta y whole square. And is our delta s. Now as delta x tends to 0, then this becomes delta y by delta x tends to dy by dx, right? So which means that it was a finite different, it was a delta of s. Now it will become a differential. So it becomes ds is equal to dx 1 plus dy by dx whole square, right? Now what we do is, this was so far so good. Now again recall what we had learned some time back, that in for any curve in xy plane, especially of this for a generic curve, we can always have t is equal to x and the rest is y is a function of t. So before it was function of x, now it will be a function of t, because of which we can have dx dy ds is equal to so I think maybe I should not fall into this
I,
pitfalls.
I was
Yes.
with this calculation in working somewhere, so I could understand till delta s is equal to this stuff. But then
Huh.
when delta x approaches to 0, so from where did we get that this del y, I mean delta y over delta x will approach to dy over dx?
Yeah, actually the thing is this is how we define a derivative, right?
Well, derivative, right.
Right,
Yes,
it in a limiting sense. Yeah, in a limiting sense.
now I understood. Right.
Yeah. So here we could then always find from here we could now. So this was just to show how it is done, and which means that if we know the limits for x, then total s will be just equal to from some x naught to x1 and then dx root over 1 plus. So this is how we can find for a general curve. But again, recall that here we are talking in terms of x as the independent variable and y as the dependent variable. But once we have parametrized a curve, our independent variable is just t. T is the only independent variable, right? This is the only independent variable. So because of which even gamma vector in say in R2 space, it becomes x of t, y of t. It's a vector now. So here when we do the same operation, then it becomes ds squared. Uh, right, we have all that ds squared is equal to dx by squared plus dy squared and all that. Now what we can do is we can divide throughout by delta t. So it becomes delta s by delta t whole squared is equal to delta x by delta t whole squared plus delta y by delta t whole squared. Now again, we make all those limiting conditions, right? As delta t tends to 0, then this becomes some ds by dt whole squared is equal to dx by dt whole squared plus dy by dt whole squared. And finally, doing all that, you can take the square root. So it becomes ds by dt is equal to root over dx by dt whole squared plus dy by dt whole squared into dt. Right, just as of now, no dt, but you can multiply both sides by dt. So it becomes ds is equal to this into dt. And so now we can integrate it from, of course, at t is equal to alpha, s is 0. At t is equal to beta, s will be have some length. So I can call it just some s. I just want it to be variable. So this s is equal to, and t starts from some alpha, goes till t, and then you have uh, again derivative. I can just call it x dot whole squared plus y dot whole square into dt. And here is where you see that length formula. So it's as if you're following along the curve and being able to get some unique, the distance from where we started. And it's always going to be positive. So in a sense that s of t is equal to from alpha to t root over. And again, let's take a look at this expression here. X dot squared plus y dot squared, the square root, seems to be some sort of a norm of gamma dot, because gamma vector was written for R2 space as x of t, y of t, and then gamma dot vector is equal to x dot of t, y dot of t. And when we take a norm of gamma of dot, then this is what that's what we get. Because as you know, the Euclidean norm, so Euclidean norm of any vector v, say v vector is equal to v1 v2 till vn. So the Euclidean norm of any vector v is defined as root over v1 square vn square till vn square. So that's what. So we are able to make some connection. So we initially we started with just R2 space, but because of this norm, we are able to generalize it. So it's like gamma vector dot t. And here gamma could be anything now. It's an element of Rn, because in this expression, this is a general expression now. Now we don't need to. It's not only for R2. We could generalize it by just putting. So this S of t is called as arc length coordinate. Arc length coordinate. So what we do is we will always map any, say, we'll always have gamma vector of say t. You'd always want it to map to gamma vector of s. Now, working with s has one advantage. I hope you understood so far. Like it's just some basic, we are just looking at distance function. So either arc length coordinate, or we can also call it as a distance function. And by its very definition, even from the mathematics, you can see norm is never less than 0. It's always greater than 0. And it's equal to 0 only if you have not traveled anywhere. So it's like even the upper limit for the integral is also alpha. So it's from alpha to alpha. So integral from alpha to alpha will evolve it to 0. So what we do is, uh,
But then how did you, I mean, move from the YT to YS? I mean, gamma T to gamma S.
yeah, so here there is, okay, I should just uh, do some use different function. That's just to remove the confusion. So you can call it something like this. So which means that we are mapping from gamma, we are taking a different map whose argument is s. So there is a very I mean, it's like some circular approach. So you choose some parametrization. So say choose some arbitrary parametrization for a curve. in terms of t, then determine s of t. Now we do the other mapping. So what we'll do from here is, say you have this gamma vector t, we had mapped here, right? So this was for the first step, gamma vector of t. Now here we determined s of t. S of t was determined. Now you want to determine, the idea from here is determine, okay, let me put in the let's name it here. So it's A, B, C. So the third step is determine t in terms of s. And once you do that, then substitute t in terms of s. So it's like t of s in gamma of t. And this will result in gamma vector of s. Some, of course, some different function. So the whole process is this. So it's like, now let's do some let's just try to delve into this little bit. So what you have is, we originally had gamma vector as a function of t, and we say that we have an equivalent mapping with principal argument as s, which is also argument of t. Now what we do is differentiate both sides with respect to t. So here what we'll have is, this is straightforward. Since we have gamma, we'll always have gamma dot of t. And in this case, we have d gamma tilde by dt. But we'll use chain rule, since gamma tilde is principally a function of s, right? Because s is its main argument. So we can of course write it as just this, which means that s it's its argument. So we'll use that chain rule. So it is d gamma tilde by ds dot ds by dt. And let's go back to ds of t. So when we take a look at this, you can always differentiate, right? ds by dt is nothing but norm of gamma dot. And we don't need to go for, we can just pull it up here. It's hidden in this expression itself. It was s of that square is equal to gamma dot like s. So it was like s dot is equal to root over x dot square plus y dot square, which is eventually norm of gamma dot. So this is what comes out to be. So we'll substitute it here. This becomes d gamma tilde by ds dot. So you see, you will have, we were able to have d gamma tilde by ds is equal to gamma dot by the norm of gamma dot. Once you have this expression, then the second part is integrate along s. Integrate with respect to s, then you will have gamma tilde of s in terms of some, right? You can, then we can always determine y, the y gamma tilde of s. So which means now we were able to move from a curve parameterized in terms of gamma vector to a curve in terms of gamma tilde with a new feature that is a function of the arc length coordinate. You'll ask, okay, but why all these hassles? The hassles, the beauty lies in this expression. If you take a closer look at this expression, right? When you take norm on both sides, say norm of d gamma tilde by ds is equal to norm of gamma dot. Gamma dot means that implies something derivative with respect to t by gamma norm of, you know the property of norm, right? The property of norm is norm of ax vector is equal to absolute value of a and x vector. And if say a is greater than 0, the norm of ax vector is the same as a into norm of x vector. And we can use this relation here in another sense, in that you can have, say, uh, x vector divided by norm of, by a, which is a scalar, and it's greater than 0. This is nothing but x vector divided by a. And we are able to use this since the norm of gamma dot is greater than 0. So this comes out to be norm of gamma dot divided by norm of gamma dot. And it's very clearly seen that the numerator denominator are equal, because of it evaluates to 1. So this is the beauty. So it seems that the rate of change of gamma tilde with respect to S always has a magnitude of 1. And that's the reason we call as arc length parametrization also as unit speed curve. Because when you take a look at it clearly, this is the derivative of mapping with respect to S is rate of change of something with respect to S. And it very much mimics what we see in mechanics, right? In mechanics, we have this rate of change of Poisson with respect to time, right? So say r vector dr by dt is velocity, and the norm of velocity is speed, right? In say classical Newtonian mechanics. So we are using the same terminology here. So the norm of d gamma vector gamma tilde by ds is always 1. And that is the beauty of arc length parametrization. So throughout this course, we will always deal with arc length coordination, always. And in differential geometry, everywhere in mechanics, we always deal with, always implied that arc length parametrization is being used. It's always implied.
I have some queries here.
Yeah,
So,
yeah.
what kind of the mapping this ST here is? Say, ST is this a mapping from R to R square or what?
No, S of t is, again, S is also a scalar.
Okay, so
S is a
then
scalar.
from R to R. So then this Y tilde is again a mapping from R to Rn.
Yeah, y tilde is again, y tilde is also an element of Rn, because we cannot change the nature of the curve, right? Curve, if it's lying in Rn, it is lying in Rn.
Yes.
So both
But
of them, it's just that S and T both are element of R.
yes. So what is the relevance of this arc length parameterization, that except that everything is positive, and I mean I could not understand the purpose of carrying out such an alternative parameterization wherein the previous one was working fine.
Yeah, that's the thing is, for this is the advantage which no other parameterization gives.
So what is the intuition behind, I mean, this thing, this result that this dy tilde by ds is equal to 1, and it's
Yeah, so
log
the
this.
intuition is that the fundamental intuition is that when you are, that the interval from where we are mapping, right? So okay, let's take a look at the intuition. So intuition is that you have this. Now let's call it something else. Now let's call it as, because S starts from 0, right? S always starts from. So let's look at the idea. So T was running from alpha to beta. This is T, domain of T. This is S. But S, you recall that it only runs from 0 to length, some length. Right? When we take a look at this, at T is equal to 0, S is 0. At T is equal to beta, it will be length of the curve. So that's the reason I'm calling it L. So any curve, right? So let's say the length to be L. So since S is the distance function, so it runs from 0 to L. So this was one mapping. And from here, so we wanted to circumvent this problem. So let's not call this. Let's call it's as if we have the same curve here, same curve. This one was gamma vector, and this mapping is gamma tilde, and the coordinates remain the same. It's the same curve. It's just how we represent it in different framework, right?
Yes, now I
Yeah,
understand.
yeah.
Yes.
So what you see is if you go from here to here, from using this gamma map. So for any incremental change in t, so say if this element, and let it be, say let's call as say delta t. Let's say we have this delta t. We have moved delta t for which this is our delta gamma vector. Right? For some delta t. What you will see is that the length of gamma vector, right? This gamma vector is not the same as delta t. Just simplest lie. I just want to give the final conclusion here. However, when you map from S domain to this domain, from to this domain in which the curve is lying, the same this part. So this one was for, say this one also was for delta t, and say this is for delta S. So it so happens that delta of S is the same as norm of, and here you will find the beauty, which means that as you are moving along this parametric domain, so S is also the parametric domain. So if you have moved by some amount here, you are moving the same amount along the curve,
Yes.
right? And we would always want to have that feature that if I'm moving some distance in the parametric domain, I should move the same distance along the actual physical curve as well. So why not we have such a domain of in such a parameter for which this is possible, and it's possible only in arc length coordinate or arc length parametrization. That is the whole point of choosing arc length parametrization, just for this feature. So we are ready to take all the pain to be able to convert in this. The only problem is that it's not always possible. It's very difficult
But
sometimes.
but then what's the guarantee that for I mean every small interval of alpha and alpha ranging from alpha to beta, there would always exist a larger interval, or could be smaller. I'm not sure. A larger interval ranging from say 0 to n. I mean, because here we
No,
are
the
carrying
thing is here. This is
because here we are carrying out.
okay. The issue,
Yeah, please.
yeah,
So because here we are carrying out two transformations. First, we are transforming T into ST, and earlier we were carrying out only one transformation. We are computing gamma T, and here we are computing the transformation of the transformation. So my question is that what's the guarantee that corresponding to this interval, say from alpha to beta, there would all we
yeah.
can always find an interval ranging from say 0 to n.
The thing is, this will always be. This is guaranteed. You can always. This is always guaranteed. It's guaranteed. Like we can mathematically prove that it's guaranteed, because the way we define this, right? Again, recall that we are not discussing about the length here. We are discussing about the length of the curve. So it's like there is no back and forth. So from going we cannot go from here to here directly. It's that we have to go from here and then use this to determine S. And that's what we saw in the flow chart, I mean the steps chart. So first we choose parameterization, then determine ST, which is again uh, requires this gamma dot values. Then we are able to expressing T in terms of S. So it's multiple, you are going back forth. I think let's do one example to be able to fully digest this. Let's do an
Yes.
example. I think that will resolve many doubts. right? So the example is again the simple example of a circle, unit circle, right? So this radius is 1, r is, oh, there's 1, and let's call it as xy, right? And let's parameterize it. So example, right? There's an example. So let's parameterize it simply. So gamma vector t, right? So say we start from here, and since we know that we can very much use this, why not have parameters, some sort of a some sort of an angle, right? So since this is a unit circle, it will be cosine t and sine t, and let t vary from 0 to 2 pi. So at t is equal to 0, gamma vector 0 is given as cos 0 is 1, sine 0 is 0. So it means that we are starting from this point. And at t is equal to say pi by 2, gamma vector pi by 2, cosine pi by 2 is 0, and sine pi by 2 is 1. So it's at this point, right? So it's like we are just following the any directed radius vector, any directed vector from the or the Poisson vector of any point on the boundary with respect to x-axis, and that is angle t, right? Now let's take a look at d gamma by dt. Okay, let's do this, right? D gamma by dt is equal to minus sine t with cosine t. Take its norm. So this is one of the rare cases where the arbitrary configuration that we choose, so this becomes sine squared t plus cosine squared t, it becomes 1. So this is one such rare case where this particular parameterization happens to be uh, unit speed, because the norm of gamma dot is 1. This is just one such rare case. It was only because we had a unit circle. What if we have some other circle, some other radius, say r? Let it be r now, radius r. So in that case, things are fine. Here you will have r0. This will be 0r. Then here it will be r minus sine t, and this will be r. It becomes gamma dot is r, right? So this is not one, not unit speed in general. So what we do is now we determine s of t, which is 0 to some t gamma dot norm dt is equal to r, and of course, so r, then dt. So this becomes r of t. Fine. So now this was the first step. This is the second step. The third was step is t in terms of s. And what we are able to do is, since s is equal to rt, you can write t is equal to s of r. This was easy because it's very simple expression. Now gamma vector t will be written as, so wherever you have r cosine, then t becomes s by r and sine becomes s by r. Now it seems that there is no explicit dependence on t anymore, so we can call it a different function y tilde of s. Right? So now check some of the property of y tilde of s. So y tilde of, right, this formulation or this parameterization doesn't have t involved, so it's like s is the independent variable. Now what you do is d gamma tilde by ds is equal to r, and then we have minus sine sorry, minus sine s by r dot 1 by r comma cosine s by r dot 1 by r. This can be written as, bring r outside, so you have r by r, which is 1, so you have minus sine s by r comma cos s by r. Now when we take its norm d gamma tilde by ds, it's sine square s by r plus cosine square s by r. This is just 1, right? You see, unit speed curve.
Yes.
right? So this is just to show how it's to be done for generic cases. But what you will see is this is the most difficult step. This is not always possible, not always easily possible. Many a time it becomes S in the relation between S and T is so nonlinear that you cannot invert it. Then what you do is in such scenario, we'll just stick with T and use all those complex expressions for determining curvature and all because I mean our hands are tied in such scenario. So this was the thing about arc length parameters, and that's the whole reason. But we would always want to have unit speed curve, right? And okay, this was one thing. Now let's move on to this understanding about tangents. So from now on, we will always assume from now always arc length parameterization. It's assumed even if we refer sometime as something as t, it's still arc length parameterization. But usually uh, the convention is to use S for arc length parameterization in all books everywhere. So we'll use S parameterization anyway. Okay, so now consider a unit speed curve and which is gamma. Now I'll remove the tilde. Now I'll just call as gamma vector as a function of S. So it's like gamma vector maps from since S will always start from 0. So 0 to some value L to some RA because arc length parameters always start with the coordinate always start with 0 at some always from some value 0. That's how we define it. Right. So So once we have this curve, then we can define something called as a tangent vector. So the tangent vector is gamma vector dot is equal to. So it's just d gamma vector by ds. That's how simple it is. So let's try to understand it for a plane curve. Plane curve means curve lying in xy plane. That's what we call as plane curve, right? So we have this gamma. So this vector, say this, it's some gamma vector some point here, gamma vector of S. So the tangent is just this tangent, as we would like to understand what tangent implies. So this is the tangent. So this is gamma vector. And as we know, the norm of this is 1, right? Because of the nature of it. Fine. So now we also want to know what is, can we have something which is perpendicular to this? This is tangent. This is tangent, of course. This will be normal or the normal to the tangent. So for this, we just go back to the definition. So you know that for any unit normed vector, unit normed, unit normed means a vector function. Say let's call it say just t vector. Say t vector is a unit norm function, say function of s. So in that case, what happens is that t vector, the norm is 1. Square both sides, it becomes norm of t squared is equal to 1. Then you know that norm squared becomes t dot t is also we can, that's how we can, so it's like dot product of itself is norm squared is equal to 1. Now what we do is differentiate with respect to s. So then what we have is using chain rule, we have d vector t by s dot t vector plus t vector dot dt vector by ds is equal to 0 because right hand side is constant. And of course, in dot product is commutative. So this term and this term are equal. They are the same thing. So we can write it as 2t vector dot dt vector by ds is equal to 0. And then t vector dot dt vector by ds is 0. So what we saw is that t vector is perpendicular to the rate of its own derivative, which means that they are normal to each other. So which means that if you have this as the tangent for a Say in this curve, right? You had this was the gamma vector. So normal can be, you have two different directions. This can also be one normal, and this can also be another. So we have two choices for normal. For normal. Right there, we have like this. This is one such thing which needs to be resolved. So you have two choices. But what we know is that normal to the tangent, at least we can say that, let's call it n vector of s, and the tangent vector we should have called, we can also call it as t vector. At least we can say that it is parallel to dt vector by ds. This is at least this we can say. Since this is parallel, we can write it as n vector of s is equal to some multiple k, not k. There's some multiple, say alpha of dt vector by ds. This alpha can be either greater than 0 or alpha can be less than 0. There's the we can have any possibility. So for planar curve, we have some conventions. Say suppose we are turning, uh, say our parameter as s is increasing in this manner. If s is increasing in this manner, then this will be the tangent vector. So normal, it's typically taken. Let me just verify. It has been some time. So let's just to get an idea about which is the positive sense. What is the positive sense? So typically what happens is this side is taken to be the, let me just check. Okay. Uh, yeah, this is the one. So this is typically taken to the positive sense of normal. And so this is the tangent. But the thing is, we do not need to stick to that. Many a time what will happen is there is a relation between normal vector and kappa and ns vector. So this was just for sake. So here what happens to be alpha is equal to 1 by kappa. So this kappa we called as curvature. So in a sense that dt of ds tells us, say for example, it tells us how a curve is curving. Right? For example, you have this curve. So the tangent is like this here. And at a different point, say this is at s, this is our tangent. At a different point, at say at s plus ds, this will be the tangent. So if we bring it to the same point, so send to the same say head of the vector. So then this is t vector and this is t vector plus t vector at s plus ds, and this is t vector. You see, right? So you see that the as you are moving along this curve, the tangent vector is rotating. Right? You can clearly see that it happens to be rotating in this fashion. So it's rotating in this fashion, but in this direction. So this is what we call as the curvature. So when we understand about something about curvature, so curvature implies how much is the, or at what rate is the tangent vector rotating. Now, whenever we talk about rate, right? So we are always dealing with scalar because curvature is meant to be a scalar. So what you do is n vector is a normal vector and the n vector is also a unit vector. In that n vector is a unit vector, meaning that norm of n vector at s is equal to 1. Right? So when we take a norm of this entire expression, so it becomes dt vector by ds is equal to kappa, norm of kappa n vector s, and you know that kappa is a scalar, so it becomes kappa magnitude of kappa and magnitude of the norm of n vector, and this is 1, so it means that dt vector by ds norm is equal to positive the magnitude of kappa. You see, right? So it means that the curvature is, it always tells us the direction, it always tells us the measure of the rate of change of tangent vector with respect to s. And that is the whole idea of what we mean by curvature. Right. So in this case, kappa is also called as this is just what we typically call as the curvature. Kappa is curvature, but uh, uh, so but we have this what we call, you also have this magnitude. So magnitude is what we typically call as the curvature, and this one is what we call as the signed curvature. Now you'll ask why is the case, why is this called signed? Because in this form kappa can be either positive or negative, but when we talk about curvature we always talk about in absolute terms, in which means that here this kappa will always going to be greater than 0. This is a
I,
distinction. Yeah.
I have a query here that what if kappa is always positive, then can we say anything about the convexity of the curve kind of thing, or
When
let's say,
kappa is always a positive, huh?
yeah.
Okay, so the thing is, the sign and all play a role in defining this, what is positive sense and what is negative sense. So as we talked, right? So in this case, n vector should be in this manner. So this we call S implies that um, uh, okay. So I don't know. I didn't understand what you are talking about. Just could you please repeat so that.
Yes, yes. So my query is related to. So can I determine that say if I compute this entire thing, say for the two-dimensional curve, and
Okay.
so say if I want to show that the given curve is a convex one, and not any very, I mean the things are always, I mean either convex or concave. So
Okay.
with this kappa thing, so can I ensure that if kappa is positive, so then the curve is always convex?
Right. Right. Yeah. Of course. So say in this representation, if we have, so in this case, if you're starting from here and following along this line, along this curve, then here in this case, kappa is going to be greater than 0. And you can clearly see that it has its convex, it is convex. But the issue, the thing is, we should not rely on this, because then you'll ask, okay, but what if I'm going from the other way around? If you go this way around, then you will see that kappa is always negative.
Oh yes, I see, I see. So if kappa is following one thing, either always positive or always negative, and
Huh.
it does not fluctuate, say from positive to negative or from negative to positive, then the things are
Yes, yes,
convex.
yes.
Yes.
Yeah. So which means that if kappa is always greater than, is always in one direction, which means that it is following a completely one curved path, and it's enclosing some sort of a, some sort of convex region. But the thing is, the way we define convexity is very different. So the way we define convexity of a function is in a different sense. So we have this function here and x and y. And so this is of f of x, right? This is f of x. So we say that, oh, sorry. We say that a function f is convex if, so say we have this x1 or x naught x1, x naught to x1, if f of x naught, right? So say what we do is, any point between these endpoints we can always map some sort of a x is equal to x naught into lambda plus 1, sorry, it will be 1 minus lambda x naught plus lambda of x1. Let's just verify this. Uh, so at lambda is equal to 0, x is equal to x naught. At lambda is equal to 1, x is equal to 1 minus 0, so it becomes 0, so x1. So which means that using this mapping, we can always find any point between these two. Now, what I meant to say that a function is convex if this is a very standard definition. If f of 1 minus lambda x naught plus lambda x1 is less or equal to lambda 1 minus lambda of f of x naught plus lambda of f of x1 for all lambda is an element of 0 to 1. Then it's called convex. So which means that it should always lie below this line. So this is what we call as, this is what this line represents. This is what this is the equation of this line 1. Line 1.
Yes, yes,
So
yes.
the function should always lie. And if this inequality strictly holds, then we call the function to be strictly convex. If it is equal to, then it's not, it's just convex, not strictly convex, which means that you are allowing this particular function to coincide with the straight line.
Right,
And this
right.
should be for all x. It should not be just for all x in that set or in the domain. Not only here, it should be for all x. Any such line, it should be possible. Any such line. Any such line. So that's how we define. So that is the reason we should kappa is can be a measure, but it's not reliable because it depends on which way we are traversing the curve. So
Yes,
that's the reason we don't express in terms of this curvature. We would not like to do that.
yes.
Yeah. So I think we are almost at the time. Uh, so yeah, I think we have been able to cover quite a lot many topics. So in the next topic, just to give you an idea, so we will discuss about space curves. Space curves mean curves in 3D, and we'll then also talk about Frenes frame. This is what we are going to deal with today. I introduced one equation of Ferres. This is one equation of Frenes equation. Then we'll have other two as others too. Right? There is one such equation, and we'll have the other two. And then, if possible, try to also finish director frame. This is the at least minimal goal, but I would also like to start discussing about surfaces, because surfaces is what we are really interested in. It has all the complexity that we would want. So things like okay, just to give an overview, there is a reason why, say for example, uh, say you take a rectangular sheet. So you take a paper sheet and cut in a rectangular form, and you hold it from this side. Right, you hold it from this side. Right? There's our hand, we are holding it. So what you'll see is, if you look at it from sideways, the paper will bend. Say we hold it from the side, right? So the paper bends, right? It bends. So this is like you are looking from the side, the paper bends due to gravity, right? This you're looking from the side, so you're looking from this side. Then this is how it would look, right? The paper is bending,
Yes,
right? But what you do is you take a paper, the same sheet, and just curve and hold it like that. So make it something of this sort. something of this sort. It's like you are just this part bring above, and there's also just turn it. Now you hold from this side. Now you hold from this side. Hold from this side. Now you'll see that the paper does not bend. Even if you hold, it does not bend now. It becomes resistant. Like even if gravity is this side, it still maintains. It still tends to be straight.
Yes. In fact, I am holding this paper right now in my hand. It's true.
Right. So the issue is it has all to do with curvature. So it is like this curvature is playing a role because you added a curvature. It made the structure rigid, or at least more resistant uh, to external force. So these all ideas come under all this. When we talk about curvatures, then we'll get to understand why is this scenario, why does this hold. Of course, this from mechanics point of view, we are able to explain it. But of course, mechanics also will use ideas from differential geometry to describe what is curvature in the first place. Then only we can formulate, the mechanics aspect of why is it so. There's one thing. Second thing is, for example, you have this sheet of paper, the same sheet, you can roll it into a cylinder, right? You can roll it into a cylinder. Just bring this part, join both these short edges, and you have the cylinder. And you can go vice versa. And you can even have this sheet and create a cone. Pick this point and just try to uh, about this point, you can make a cone. You'll ask, okay, I will do this, but you cannot you cannot make a sphere out of it. Sphere, not possible. You cannot create a perfect sphere without cutting, right? This is without no cutting, no cutting. So at least the going forward direction, no cutting. This also going forward direction, no cutting. Here, cutting is involved. So I ask, okay, where does these ideas come from? So these ideas actually come from why you can have a sheet, flat sheet, and then make it a cylinder or cone, but not sphere. These all ideas is it's related to Gauss curvature, and we'll understand why as we'll try to do within the next 2 or 3 lectures. Try to arrive at that point to explain why is it the case.
So
Yeah.
do you want me to refer some of the chapters of the book you have given in that folder, so that when I come to the next class, so I know a little bit better about these notations
Sure,
and
sure, sure. Definitely, I would really urge you. Yeah, just that books are in the reference books folder.
so which chapter should I refer to those books? I mean,
This will be covering. What I'm doing a rapid review. So it won't be possible to finish, but it is like first 2 chapters at least.
okay, okay, yes, I'll do that.
So yeah, we are trying to do a rapid review, even some parts of third chapter as well.
Okay,
So I'm just teaching only. We are only discussing what is relevant to us. So in the previous course, we went very deep into all the derivations and all.
yes,
Right now, just skimming it because we have a lot of other materials to cover. We actually want to understand mechanics. Uh, how do we use it to derive models for all those structures? So that is the whole reason.
yes, yes.
Yeah. So yeah, I think we should close it for now. I'll also in the same folder you will also find the previous lectures that my notes for the previous lectures.
Sure,
I
sure.
mean the last course here. I'll just put it up there in the same folder.
Yes. Thank you so very much.
Yeah,
And
yeah, welcome. Yeah, thanks a lot, yeah, for attending
thank you so much.
and
Bye bye.
keeping it very lively.
Yeah. Bye.
Yeah, bye, bye. Yes, I'll just stop recording.